Today we're going to go into more details about recursion. If you recall, early on in the semester I showed you a little bit about recursion using the SDBA website, and in fact we've already used it in one of the labs earlier. But now we're going to go into more details about what actually recursion is. So recursion is a way for us to break a big problem into smaller problems. Basically, we assume that we know how to solve the smaller problem, and then now based on the result of solving the smaller problem, we can build on it and build the solution for a bigger problem. So usually it is in terms of numbers, where it is one less than the other, but it's not always the case that it's numbers. It could be other things as well. So you're trying to solve the problem for p of n by solving the smaller one, pn minus 1, then pn minus 2, and so on until you go down to p1. So the solution of p1 then feeds back into p2 and p3 and p4 all the way back up to p of n. So one example of this is if we're trying to do the power of x to the power of some number. Okay, so you've got x to the power of some number. So let's say if you've got 5.4 to the power of 3, what you need to do, you need to multiply that 5.4 by itself 3 times, right? So we know that if n is 0, anything to the power of 0 is 1. So that is what we call the base case, and we return 1. But if n is bigger than 0, then if we know the power of n minus 1, then we can just multiply with x again, and we will get x to the power of n. See, the power of that means x to the power of n minus 1 times x is x to the power of n. So this makes the whole situation very simple, because you've got this very simple case which we call the base case, and then we've got this case that we call the inductive case, where you are building on an earlier or a smaller problem and solving it for the one larger than that. So this program, which is included in the resource files that I have uploaded to MMLS, will have this program in there, and you can try it out. You can change these numbers so that you can see what the results are. So we are doing this recursively, means that a function calls itself. See, over here we had power calls power, right? So this is when you have a recursive function. A recursive function calls itself. So each recursive call is solving the same problem but for a smaller question. Okay, in this example, a smaller number, one smaller. So the solution for the smaller problem builds into the solution for the bigger problem, and then we have that base case where the problem is so simple we just know the answer to it. So in the case of this power, x to the power of 1, x to the power of 0 is 1, no matter what x is, right? So that's the base case. So this is where you know the base case, and then eventually you will get to the base case, because you keep subtracting 1, subtracting 1, subtracting 1, you get to the base case. And when you get to the base case, then it winds back. So when you're trying to make a recursive solution, then you have to think about these 4 questions. So how are you going to think of the problem of the smaller one of the same type? Okay, meaning I've got this bigger problem. How do I make the solution for this bigger problem with a slightly smaller problem? The solution for a slightly smaller problem. So then how does each recursive call diminish the size of the problem? In the case of our power, we diminished the number by 1, right? So until we went down to 0, and then we knew the answer for that one. So what instance of the problem can serve as the base case? That is, in our case, in that example there, it was when we reach 0, and we knew that anything to the power of 0 is 1, and that's the base case. And as the problem size diminishes, will you reach this base case? So it has to be able to reach the base case, otherwise your program ends up in an infinite loop. So you have to think carefully to make sure that, oh, it will reach the base case. And in the case of our example here, this example here, right? We knew that if each time we're subtracting 1, this is a number, okay, it's an unsigned number, which means only positive numbers, okay, no negative. So if I keep subtracting 1, eventually I'll get to 0, okay? So that's why I can be guaranteed that I will reach that base case, and that causes it to stop, okay? So here is another example. In fact, this is the example that I showed you on the SDBA website earlier. It's to compute the factorial of an integer. And as you might recall, the factorial of n is n times n minus 1 times n minus 2 times n minus 3 times n minus 4 all the way down to when it reaches 1. So for any integer greater than 0. And the factorial of 0 is 1. So here we have our base case, and here we have our recursive case. Okay, so the recursive definition of the factorial n is factorial n equals 1 if n equals 0. And if it's not 0, then it's equals to n times the factorial of n minus 1. Okay, so if you have any number bigger than 1, we just have to find the factorial of the one smaller and multiply by n. Okay, and if you have the number 0, then you just return 1. So it will recurse until it reaches this base case of n equals 0. So here we have the function. Okay, this is going to compute the factorial of the non-negative integer n. So the precondition is n must be greater or equal to 0. If it's not greater or equal to 0, then you end up going into an infinite loop because you never reach n equals 0, right? So the postcondition is none, so we return the factorial of n. N is unchanged, okay? So we're just going to return this. So this is our base case. If n equals 0, we return 1. Else, we return n times factorial of n minus 1. So what happens here? If I run the program and I say, okay, I'm going to calculate the factorial of 3, so it's going to reach that, it's going to look here and say, oh, n is not 0, so I'm going to return n times factorial of n minus 1. So then it's going to call factorial of n minus 1, which is factorial of 2. Okay, factorial of 2 is going to call 2 times factorial of 1. Factorial of 1 is going to be 1 times factorial of 0, and factorial of 0, we've reached the base case, which is return 1. So we're going to return 1 to here, which will then give you the 1 times 1, and return 1 to here, which is 2 times 1, and return 3, return 2 here, and so you have 3 times 2, and return 6, and it prints out 6. Okay, so this is the factorial of n. So what you saw earlier was what they call a box trace, which is a systematic way to trace the actions of a recursive function. So each box shows you one function call, which causes an activation record on the system stack, and this contains the function's local environment at the time of the call to the function. So it remembers what the different values of the number n is. See here, number n is 3, number n is 2, number n is 1, and so on. So it remembers that in the activation record. So you have a particular box is like n is 3, and the answer is factorial of n minus 1 equals what? We don't know yet. We call the return what. So then it goes on to the next level. So a function's local environment, you have the local variables, you have the actual arguments, you have the return address of the calling routine, and you have the value of the function itself. So you can see that this will go from here to here to here to here, and then return, return, return. Okay, So that's what's going on there. So if we look at the video, this is the video I showed you previously, then you can see that it's going to do that. And so these two places, we're going to look at it.
First, we have to declare our function prototype. This is the function factorial, which returns a long integer. It has an integer variable n. It is the only argument of factorial. This is main, and she is being declared as an integer type. She has an integer variable n.
Hi user, what integer value you would like to find the factorial of? 3. Factorial, come here please. 3 is larger than 0, so we do 3 minus 1, which is 2. Factorial, come here please.
2 is larger than 0, so we do 2 minus 1, which is 1. Factorial, come here please.
1 is larger than 0, so we do 1 minus 1, which is 0. Factorial, come here please.
0 is not larger than 0, so we return 1. The answer is 1. I'm free.
1 is multiplied with 1, which is 1, so the answer is 1. I am free.
Now, 1 is multiplied with 2, which is 2, so the answer is 2. I am free!
2 multiplies 3, which is 6, so the answer is 6. I am free. Hi user, the factorial of 3 is 6.
So here is the same problem as we saw acted out earlier. This time we are showing you the C code. Remember, this is from the SDBA website, which is all in C, not in C++. But the principle is the same, and if you look at the factorial function, it is pretty much the same function. Okay, so first, in the main, it makes a variable n. Okay, so in this example, it's at FFE2 in memory. Then it prints, it asks the user what integer to find. So the user types in this case 4, and it prints the 4 factorial equals what? So it has to call the factorial of n. In this case, n is 4. Okay, so then n is greater than 0? Well, yes, because 4 is greater than 0. So now we are going to call factorial of n minus 1, which means 3. So 3 is greater than 0. Yes, 3 is greater than 0. So now it's going to call the factorial of n minus 1, which is 2. So now 2 is greater than 0. Yes, it's greater than 0. So it's going to call the factorial of n minus 1, which is 1. N is greater than 0. Yes, it's greater than 0. So it's going to call the factorial of n minus 1, which is 0. 0 is not greater than 0, so it's going to return 1. So that 1 is going to go back to the previous invocation, like so. There, we remembered that it was the factorial times 1, right? So that's 1 times 1, which gives us 1. And now we are going to return it, this one, to the previous invocation, which now gives you 1 times 2. 1 times 2 is 2, so it's going to return that to the previous invocation, which now gives you 2 times 3, which is 6, and return the 6 to the previous invocation, which returns 6 times 4, which returns then to the previous invocation the answer 24, and we will print 24. So that's what happens there. Okay, this is a little bit about recursion versus iteration. In a recursion, you have a control structure where you have a selection, achieve repetition through repeated function calls. Whereas in iteration, you repeat explicitly, like using a for loop or a while loop. Termination in recursion is when you reach the base case. Termination in iteration is when your for loop or while loops end. And you get an infinite loop in recursion if you never reach the base case. Whereas in iteration, it happens if your continuation test never becomes false. In recursion, you use more memory usually because each recursive call causes a whole activation record to be created, whereas in iteration, it usually has less extra memory because you don't keep calling the function again. So that is factorial by recursion. Okay, now we are going to look at another example of recursion. In our previous example, you noticed that the function returned a value and we used that value in the recursive call to produce the answer. In this particular example, we're going to have a void function, which means it does not return a value. Instead, we're going to have it do something which will be recursive. So the problem we are going to solve here is that you've got a string of characters and we're going to write it in reverse order. Remember, we've solved this problem before using stacks in an earlier lesson, in the stack lesson, right? And now we're going to solve it using recursion. And as you might recall, I told you that a stack is actually made by the operating system for every program for function calls. So the recursive solution actually uses a stack, but you don't write the stack. The operating system does the stack for you. So the recursive solution is going to diminish by 1 the length of the string to be written backwards. And the base case is the empty string. Well, writing the empty string backwards is simple. You just don't write anything. So write backwards s is going to call write backwards s minus the last character. So the pseudocode is like this. I'm going to write backwards this input string s. If the string is empty, I don't have to do anything. I'm done. This is a base case. Otherwise, we're going to write the last character of s and call write backwards s minus its last character. Okay? So that way I'll be writing the character backwards. Well, let's look at the actual C code, C++ code, sorry. So here you have write backwards s. It returns void, so we are not returning anything. We have a string s and the size of s. So if size of s is 0, that's the base case. We don't have to do anything. And so if it's not 0, we want to write the last character, so we call this substring of size minus 1 and of length 1. So this in effect says write the last character. Then we call write backwards with s with the size minus 1. So we're making the size 1 smaller. So when it calls that 1 smaller, then it's going to do the next character. So looking at the box diagram, what happens if we run it with cat? Okay, cat size 3. Okay, so it's going to first print T, right? And then it's going to call itself with size 2. So it's going to be the C and A, right? So it's now going to print the A. Then it's going to call itself with size 1, which is it's going to print the C. So, sorry, the T. Okay, so it's going to, sorry, the C. Okay, that's a size 1. That means you're looking at this C. So we have printed TAC because here we printed the T, here we printed the A, and here we printed the T. Okay, so CAT becomes TAC. All right. So the new invocation begins execution here. We size 0. We return. We come back, and we come back, and we come back. Okay. So the invocation completes. Control returns to the calling program, and we have printed the cat backwards. Now, you often might make mistakes, right? You always make mistakes writing programs, you make bugs, and so you have to debug it. So recursive programs can be a bit confusing to debug. So one way is that you could use some cout statements in the middle of things to say, oh, actually what's going on here? Okay, oh, let's put a cout here and see whether I call it correctly and so on. Okay, cout here, I'm doing the do nothing thing. Oh, cout here, I'm doing the so that at least I know what I'm going to do in the program. So that way it'll help you debug. After you've already debugged, then you removed all those cout statements and you can use the write backwards. Another way, of course, is to use the GDB debugger that's provided in Linux that I showed you in tutorial 1. If you've forgotten how to use it or you didn't look at it earlier, please do ask me for help during the next lab. So, as we saw earlier during our little detour into C using the SDBA website, some recursive functions are not so efficient as the iterative function. So sometimes it takes up too much memory. In fact, if you're going to do the paint bucket fill using recursive with a large picture, you could easily run out of memory because the paint bucket fill creates a whole new stack frame for every single pixel. So if your picture is like 2 GB picture or something like that, or actually not even 2 GB, even if it's a 500 meg picture, that means 500,000 function calls. Okay, so that would make it really inefficient. So the overhead associated with these function calls will often make it inefficient, and some recursive algorithms have inherent inefficiency because they are recalculating things. So if you can do a clear and efficient iterative solution, do that. But sometimes the iterative solution is just so much more complicated, and also the recursive solution doesn't really go through so many recursive iterations, so it's all right. Okay. So, for example, if you're doing parsing, recursive solutions often is clearer. So a recursive solution solves a problem by solving the smaller problem of the same type. So remember, these are your 4 questions that you need to ask when you are going to define a recursive solution. So how do you define the problem in terms of the smaller size? And then how does each recursive call diminish the size? Remember, in the factorial, we diminish the size by 1 number. Right, 1 integer each time round. In the string, we diminish the size by 1 position in the string each time round. And then what instances of the problem can serve as the base case? And as the problem size diminishes, will you reach a base case? So those are the 4 things you must consider to construct your recursive solution. So you must assume that a recursive calls postcondition is true if if precondition is true. Okay, that means that if, like I say, it must be a positive integer coming in, then definitely it will complete and find the solution. Or we say, it must be an array of characters or something like that. Then it must be that the postcondition is true. Okay, So you can use this box trace diagram that we showed you to figure out if the recursive what it's doing. And the recursion can also use to solve problems where the iterative solutions are difficult to conceptualize. For example, parsing, as it's an easier solution than using a stack. Alright, so now there are some recursive solutions that are much less efficient because of this overhead of the function call. So if it is possible to solve a problem using iteration, you probably want to do so. That is, if it's possible easily. Sometimes it's always possible, but sometimes not possible easily. Okay. There are many other extra examples in this set of slides, and you can look through them to look at what other uses of recursion. For example, what do these rabbits have to do with recursion? Ooh! So do download the slides and take a look at them.